Math 2414, Differential Equations, Video 3, Initial Conditions. At the end of the previous video, I mentioned that the solution that we got, the one that still had the plus c in it, was called a general solution, meaning my solutions look like this. But that if you put a particular value in for the c, then you get what's called a particular solution. So under what conditions would we get a particular solution as opposed to a general solution? And the answer is if you're given what's called an initial condition. An initial condition is simply a set of values that has to satisfy the function initially before you even solve the differential equation. For example, solve the differential equation assuming the ordered pair 1, 0 is on the graph of y equals f of x. This is similar to saying that f of 1 is equal to 0. So initially my function has to do that, but it also has to do all this as well. So if we have an initial condition, what do we do with it? The answer is we solve the differential equation generally, so get the solution that has the plus c in it, and then use the initial condition in the solution to find the missing value for c. Then we'll have our particular solution that doesn't have an unknown constant. But first we have to solve the differential equation. This one is separable. It is a ratio of a function of x and a function of y. And it doesn't matter which is on top and which is on bottom, as long as it's a product or a ratio, quotient if you will, of a function of x and a function of y, then the differential equation is separable. Let's not dilly-dally in separating this. We could separate it the same way we did in the previous video by multiplying both sides by dx to put it over here, and by multiplying both sides by this denominator to put it over here. Equivalently, you can think about it as cross-multiplying. But either way, when we separate, we're going to get 2y plus cosine y dy on one side. We'll put it on the left since the dy is already over there in the numerator. And on the right, we get 6x squared dx. So the separation wasn't that hard there. Now we just have to integrate. These integrals are easy. Just a word of warning. Any integration technique you know is fair game. Integration by parts, trig integrals, trig substitutions, partial fractions. But this one's easy. The antiderivative of 2y is y squared. The antiderivative of positive cosine y is positive sine y. And remember, when we're doing this move, we only need to use plus c on one side, because if we put it on both sides, we could just put them on the same side, merge them into a single constant. On the right side, we get the integral of 6x squared dx, which is 2x cubed. And then we'll put the plus c there. All right, so the integration wasn't that bad. But our third step says, if possible, solve for y. It is impossible to solve for y here. It's impossible to solve for a variable that is both simultaneously inside a trig function and outside a trig function. There are ways to approximate values. If you were solving an equation, a particular solution, like we knew a number here, there'd be a way to possibly solve for y numerically if this was a number over here. Take a class called numerical analysis if you want to know more about that. But in this case, this is a perfectly acceptable solution. Even though it doesn't say y equals, we say that this equation implies a function y equals f of x. And if you wanted to get super nitpicky and go to the core definition of a function, each x is paired with exactly one y. If I put a value for x here, is there a unique y here? Well, if we limit the range of values that y can assume, yeah. But for now, let's just assume that this equation, although we can't solve it for y, implies a function y equals f of x, with appropriate restrictions, if you will. But we're not quite done, because we need to make sure that our solution contains this ordered pair on its graph. In other words, we need to make sure that this equation is true when x is equal to 1 and y is equal to 0. So if we use the initial condition, let's substitute 0 for the y's. So we get 0 squared plus sine of 0. And 1 for the x. So we get 2 times, something's going funny over here. I don't remember this before, but this is, I must have made a mistake earlier when I was prepping because I thought this was 3x squared, not 2x cubed. Wow, that was a boneheaded mistake I made earlier. And if I hadn't said anything, you would have never known I'd made it. But I'm human. Back to the task at hand. Put the 1 in here, we get 2 times 1 cubed plus c. And now the only unknown is the constant. We can just solve for it by evaluating everything. Sine of 0 is 0. 0 squared is 0. 0 plus 0 is 0. 1 cubed is 1 times 2 is 2. And if we solve that, we get that our constant has to be negative 2 to satisfy this initial condition. Therefore, our particular solution to this differential equation is y squared plus sine of y is equal to 2x cubed, and our constant is minus 2. And that's how you use an initial condition. Let's go ahead and add that as the fourth step. If an initial condition is given, use it to find the constant c.